Good afternoon, everybody. Sorry I'm a little bit late. It's the unending presentation week this week. I'd like to introduce you to Dakota Scott. I've been working with him for about a year on a project to build a tracking solar collector for urban and suburban applications. The idea being that the tracking function of it allows it to be a lot more efficient than what you get from just a fixed solar collector. So that said, why don't I let him get talking about it, and thank you for coming.
All right, so the design and feasibility of a PV photovoltaic, which is basically solar panel system for urban and suburban applications. So basic overview, I'm going to go over the background, then the goals of the project, some useful background information, design and analysis. There's two pieces of this, structural and electrical. Then the experiment itself, the design of the experiment, the data collection, and the data analysis, and then my results and conclusion. So a bit of project background, currently only 0.46% of the United States power production comes from solar sources, but it's a quickly growing field and technology. As you can see from this chart, just cost per watt has decreased exponentially. And as cost decreases, the efficiency of these systems is also increasing constantly. So they're becoming a lot more viable, and many places, as far as the green energy movement, a lot of places are beginning to offer subsidies for using solar energy, which helps out. Most residential PV systems are stationary, but a solar tracking array can increase your efficiency from anywhere from 20 to 40%.
What's the vertical axis thing? What is the cost in 2013 for PV?
2013 for PV.
That number down there, 0.34 a watt?
I think so. I can't see it on here because it's a smaller screen. I was expecting that.
Okay.
But so the goals were to design a system capable of tracking the sun in two directions: the altitude, which is the elevation, and the azimuth, which is how far the sun moves across the sky, east to west. The design was supposed to use low-cost components to keep costs down. I was also developed an experiment to compare solar tracking to a stationary system, and then analyze the economic benefit with a rate of return analysis. So the rate of return analysis for this experiment was actually a differential rate of return. So the additional cost that for a tracking system subtracted from the cost of a stationary system was used as the initial investment, and then the greater amount of savings you get with a tracking system versus a stationary system was used as the savings per unit for the rate of return analysis. And then from this I determined the feasibility of solar tracking arrays for personal and small scale commercial use. So just some information. As the sun moves across the sky, it's not equal throughout the year. So in the summer, it takes a longer trip throughout the sky, moving about, and this scale on the left is actually for Lexington, Virginia. It shows the azimuthal angle throughout the year and the elevation angle throughout the year. So in the summer months, it actually moves about 240 degrees across the sky and an elevation of about 75 degrees. And in the winter months, it's around 120 degrees across the sky with an elevation of about 30 degrees. This is important because we took all of our measurements around the equinox period, which is when it's about average. It moves about 180 degrees across the sky. And since I wasn't able to take data all year, using the equinox is a pretty good average, shows the average insolation throughout the year. So the reason this angle is important is because of the projection effect, which is your power loss and your radiation loss due to the angle of the sun. So say you're looking at a certain amount of space that sunlight goes through. It has an energy density of about say it has an energy density of 1 kilowatt per meter squared. If it comes straight down the surface, all that energy density is put on that 1 meter squared, so it gets all of it. If it comes in at an angle, that energy density is actually spread across the space that it hits, so it's not as dense anymore. And it's equal to 1 minus the cosine of the angle. So for the equinox months, it's about 180 degrees across the sky. that split, and for here, since it has the horizon effects like the mountains and buildings, it's about 150 degrees. That divided by 2 is 75 degrees in the morning, 75 degrees in the evening. If you take the cosine of that angle subtracted by 1, you get about approximately a 75% power loss in the morning and evening. So here's some background on photovoltaics. Basically, they run on the photoelectric effect, which is as sunlight hits two different natured semiconductors. One is negative type and one is positive type. It creates a potential difference in electricity, which causes current flow. The most common type used for solar panel material is crystalline silicon. Our panel is actually multi-crystalline, which is less expensive than a monocrystalline, but monocrystalline are more expensive because what is required to grow large crystals of silicon. The typical commercial efficiency for a silicon wafer base is about 12 to 16%. For ours, it was 16%. So I was faced with a design issue. So we already had a single axis tracking frame. I had to convert it to a dual axis tracker. I wanted to maintain the strength and durability of the design because the original design was meant to endure large wind loadings. I wanted to use affordable components. I wanted to include built-in rotational limits. So as it tracks the sun in the azimuth direction, you could set it for the time of year not to track too far one way or the other. And if you have space constraints, say you don't want it to hit something, you could also limit it that way too. And I wanted to include housing for the electronic components so that it was basically weatherproof. So the previous work, this is the original frame that I had to deal with. It has just tracks in the altitude, so the elevation. It uses a single lead screw powered by a 12-volt DC motor. It was a simple but sturdy design. It used a basic control logic, which I had to fix, and utilized this photoresistor circuit to track the sun, which I also ended up using. So here's my design. It had the wheels on the bottom, elevated it to return. It's made of 4 main components, so the drive wheel, the grounding assembly, limit switches, which are included on the grounding assembly, and then the solar tracking components. So when developing the ability to turn, I was initially faced with an issue whether to do inboard or outboard design for allowing to turn. Inboard would put this motor actually in the center of the rig, and this had a benefit because it had all the electronic components centralized and it took up less space, and the wires that were going to it had less of a chance of getting caught under a wheel or something, but it also had a lot less torque. Using the outboard design, which I actually went with, you have a lot more torque and it actually is a slower turn, which is beneficial. So the gearbox I designed was using I designed and fabricated this gearbox. It uses a worm gear, which is beneficial because it's self-locking, so if the wind does hit this, it's not going to move if this wheel's locked in place unless there's motor input, which allows it to turn. It's a 20-to-1 gear ratio, which increases torque, and it also decreases the speed, which is beneficial because the sun moves very slow across the sky. I also wanted this rig to move slow, because if it moves too fast, I run into control issues and possible oscillation. So if it moves too fast, it will overcorrect towards the sun and have to overcorrect back. So I wanted to eliminate that. So the design wasn't just built arbitrarily. I did some analysis first to make sure that it would actually turn the thing when I got it built and put it up on the wheels. So the torque calculated coming out of the gearbox is about 668 inch-pounds force. If this is greater than the max amount of torque that can be applied to the wheel due to friction force, there's a possibility for slipping. So to calculate this, I divided the weight of the total rig, which is 224 pounds, which comes out to about 56 pounds per wheel. I also experimentally determined the coefficient of friction for the wheel on concrete. It's about 0.67. And to turn this into a torque, I took the force of friction times the radius of the wheel, which gives me a maximum torque that can be applied to the wheel of 112. So I could, the torque from the gearbox was greater than this, so slipping could occur. To ensure that it didn't, I had to do another torque analysis. So if the T max that you can apply to the wheel is greater than the resistance torque that you get from the other 3 wheels rolling, then no slipping will occur. So again, the weight divided by 4, and I experimentally determined the rolling resistance of the wheels I used to be 3.91 pounds underneath underneath the weight of 56 pounds. So the torque resistance is just the force of resistance times the number of wheels, which is the three other free rolling wheels, times the radius, which is 3 inches, which gives me 35 inch-pounds force. This is much less than the T-max, which was 112, so no slipping was going to occur. So the next component was the grounding assembly. The purpose of this grounding assembly is that it can be bolted to a concrete structure or grounded plate. It helps prevent the system from walking, so as it moves back and forth, preventing it from moving either a little to the left or a little to the right. And it also assists with wind loading, any wind loading that might be. And included in this, I had the limit switch, which limited its rotation, and it was a very simple design. This right here has a limit switch on each side of it, and I just put a bolt through this arc plate. So any angle that you want, so say you want it to only move 90 degrees on each side, place a bolt right here and a bolt right here, and it will hit the bolt and activate the limit switch, and it will stop its rotation. It will send a signal to the microcontrollers. So to ensure that it was still had the same structural integrity that the original design did a finite element analysis, modeled for wind speeds of 100 miles per hour at the max angle, so as it's all the way up, so the wind is hitting straight against the panel. The high stress areas were the wheels, and it turns out the front wheels lifted off the ground. This right here is actually deflection exaggerated by a scale of 13, and you can see that the front wheels do lift up, and this grounded plate, which was assumed to not move because it's bolted down, actually does take quite a bit of deflection away from the back part, and you can see the massive moment created by the panel getting hit by the wind, because since these are on sliders, all of the horizontal force is actually coming through this slider right here, so it puts a massive moment down here, which you can see causes some bending. There was actually, we recently found an issue with the finite element analysis. Most of the design is free of yielding, but there is a region of artificially high stress. We determined this to be most likely a contact issue, and to ensure that the rest of the model was still sound, that there was nothing wrong with the model, I did a hand calculation to see what the stress in one of the areas would be, and then I compared it to the model, and there's a 6% difference, so it's actually a fairly accurate model. There's just this one area of artificially high stress, which is about 76,000 psi. The rest of the design stays under around 31,000 psi, and the yielding strength of structural steel, which is the material used to design this, is 36,000, so it is below the yield strength. The issue was with the original design. I actually wanted to look at just my design to make sure that it stood up to the wind loading. There was a lot of pressure on the back wheels, so I looked at isolating just the gear wheel, the driving wheel, and it actually has a max pressure, a max stress on it of 21,000 psi, which gives it a safety factor of about 3 for structural steel, which is very good. So now I'm going to get more into the electrical components of it. The solar tracking circuit, which I developed, uses photoresistors, and the concept behind a photoresistor is that as the sun shines on it, it reduces in resistance. So these were used, there was 2 used, as you can see, at an angle, and as the sun hit one, it would cause resistance to drop, which would send a signal to the microcontrollers to turn towards the sun in that direction. I also included ballast resistors because since when the sun hits it, it reduces resistance. It was causing more current to go through the system, and was actually draining the batteries of the Arduino, so I wanted to reduce the power consumption. So the way the sensor reading works is that if all of these are equal, say the sun is hitting equally on both resistors, the output from a 5-volt source between the two should read to be 2.5 volts. So if it's above or below 2.5 volts, the system knows that it needs to go one way or the other to track the sun. So here's the solar tracking control logic I used. I used Arduino microcontrollers because they're relatively cheap and they're easy to use. There's a lot of information out there on them. I had 2 different trackers that ran simultaneously, one for the azimuth direction and one for the altitude direction. The The azimuthal one actually is the driver controlling the altitudinal one. So this basically just means that when the azimuthal microcontroller turns on, it sends a signal to turn on the altitudinal controller. And when the azimuthal controller turns off, it sends a signal to turn off the altitudinal controller. And I had it programmed to reset itself at the end of each day. So once it hits the end of travel, it wait a certain amount of time and swing back around to catch the sun early in the morning. So just to walk through this logic right here, I had it attached to a real-time clock so I could have a time range on it, as well as having the limits on the angles that can move. I could also have a time range, so if you wanted to set up a timer. So if it's within the time range, it sends a signal to turn on the altitude controller. Then it asks, is switch 1 hit? If not, then is switch 2 hit? If not, that means it's not hitting either limit, so it's good to go. It takes an average of 5 readings, which is important because the original design for the control system, we just constantly took readings and would adjust based on that. And the issue with this is, if someone just happens to walk in front of one of the sensors, it automatically thinks that it needs to move away from that direction towards the sunlight. So it was constantly adjusting for just little shadows cast on the thing. So using an average reading prevented this from happening. And then it would see whether it was greater or less than 2.5 volts, which would send a signal to move one way or the other and would reset the whole thing. So the experiment design, since the experiment was designed to compare the dual axis tracker to a stationary mount, I set them up side by side from sunrise to sunset. The control panel right here was actually oriented directly south and was set for the optimum angle for the time of year, so it had maximum power production. And like I mentioned earlier, since we were doing all these measurements during the equinox, it's a good representation of the average yearly insolation. The data collector I used was actually a Campbell Scientific 01000 data collector. It was used to record a differential voltage, which is the voltage that the solar panels was producing. It was programmed to take a voltage reading every minute, and then it recorded the average over 5-minute intervals. So every 5 minutes, it was a data point throughout the day. So to collect the data, because the data collector records volts, and I wanted to record the power they produce. So I had to create a circuit that allowed me to do this. Since the conversion from volts to power is V squared over R, I had to come up with a resistance that maximized power. So if you have no resistance, you just measure the open circuit voltage, there's no power reduction. And if you have a short circuit where there's no resistance, there's also no power reduction. In between those two is a resistance that actually maximizes power output, and this is the Thevenin resistance, which I use an adjustable rheostat to set it to the Thevenin resistance, which was 2.546 ohms. And after that, I had to record the voltage difference across that resistor. And since the data logger only goes up to 2500 millivolts, I had to find a way to split the voltage because the voltage was actually in the volt range for coming out of the solar collector. So I used a 111 voltage divider across it. So basically this means that for when I'm going to calculate power, it's going to be my actual power for my actual voltage coming from the solar panel is actually 11 times what I recorded. And to find power, it's 11 times the voltage recorded squared over the Thevenin resistance that I set. So here's the actual collected data. Here's what it is for a cloudy day. As you can see on both of them, that early in the morning, you have this spike because it goes straight towards the angle of the sun and adjusts and stays about level all day, while the stationary one is very dependent on the angle of the sun, maximizing and equalizing the two of them right here around noon, and then dropping back off during the evening. This is one of the benefits of solar trackers, is that there's steady power production throughout the day instead of a peak at noon. And as you can see on the cloudy day, in these areas where there's no incident sunlight, because that's what provides solar panels most of the power is incident sunlight, they're about equal. And I split it into cloudy and sunny days because it was actually pertinent for the economic analysis, because the amount of average fair weather days in this area is broken into completely sunny days and then partially cloudy days. So for the data analysis, I had to go from my voltage that I recorded into savings per year, which required a bit of converting. So the voltage recorded times 11 for the voltage divider, squared over the Thevenin resistance, like I already said, gave me the power. To get this power into kilowatt hours, which is what electricity is usually rated in, I had to take power times that recording interval that I mentioned earlier, the 5-minute interval that it records. So every data point was times by that 5 minutes to get a kilowatt hour. The summation of all these data points per day gave me the kilowatt hours produced per day. And for the solar tracker on a sunny day, it produces about, one panel produces about 1 kilowatt hour of energy a day. So to find the kilowatt hour per year, I took that per day times the amount of fair weather days in a year for this area, and that gave me per year. And then the kilowatt hour production per year times the cost of electricity for Virginia is about 10.5 cents per kilowatt hour. That gave me the savings per year. And it's important to remember that this is a differential rate of return analysis. So the initial cost being how much more it costs to buy a solar tracking array versus a fixed array is the initial cost, and then the money earned per year is the difference in savings between the two per year. So differential in savings per year is about $6.17. This over the warranted life of the solar panel, which is rated warranted for 25 years, and then using the initial cost of the additional tracking components, which was about $1,300, is a differential rate of return of about negative 13%. So this basically means that solar tracking, at least on a personal scale and on a small scale, is not economically feasible. A stationary panel would be better for residential use, and that's why most people use it for residential use. Even though government subsidies may make it a little bit more viable, and it does offer more consistent power throughout the day. So if for some reason you use it for specifically power production, so like when your power goes out and you're not worried about the economics of it, it does have a better power production throughout the day, and that does mean it requires less battery storage. Here are my references, and special thanks to Marco Floyd. He's who runs the shop down in Nichols. He's really helped me out in the lab when I was putting together this thing and designing it and fabricating it. Special thanks to Mike Cullen, who helped me out with the solar panels. Colonel Newhouse actually provided me with the data logger and showed me how to use it. And then my VRs, Eric Johnson and Zhao, helped me set this up while I wasn't here. So they went out and set everything up to help me collect data while I wasn't here. So thanks to them too. So that's it. Are there any questions? Yes,
I'll
sir.
ask you a question as a complete and total novice. I didn't understand why you were taking data every 5 minutes and then do all the math calculations. Why didn't you just put a battery on the two of them and see how much power it generated for your battery over the course of the day?
The purpose of doing that was to log the power throughout the day. And if you use a battery, that's why I use the whole Thevenin equivalent. This way I can set it up to have maximum power production. And I can also see, a battery wouldn't allow me to see how it responds throughout the day. This actually allows me to see how the two respond throughout the day. It shows me these curves to see that I'm actually getting a benefit from having it set
But
up.
isn't it the end result, the amount of power you put into a battery, that really what you care about? Or could you do them side by side? Do your 5-minute calculations and then compare that to a battery?
I guess I could have put it through a battery, but I could have put it through a battery, but that wasn't what the scope of the project was. I actually wanted to analyze and see what it was looking like per day as comparatively. Yes.
Do you think on a commercial scale this might be more economically feasible as well as practical?
What size commercial scale?
I mean, we're I guess on the opposite end of the spectrum. We're talking about a
Like
single
for
house,
large,
like let's say on the size of like a Costco building or something like that. where the-
Costco building.
you know,
Actually,
like a Walmart supercenter, something that could cover a large amount of area.
it could be more economically feasible. It there's 3 types. There's stationary, single axis tracking, and dual axis tracking. And with each of them, you get amount of energy per land. When you have multiple dual axis trackers, you actually need more land than you would for stationary because they move and they crash out of each other. So most power production, like solar farms, if they use tracking at all, it's usually single axis because that's the most efficient. When you get into dual axis, you actually the amount of land required to produce it kind of negates some of the energy that you're producing. They do produce more energy. Dual axis trackers do produce more energy, but you also require more land to produce that amount of energy.
So it's more of a situational variable of whether these are practical?
Yeah, so it very much depends on the scale. Yes?
Could you explain again the 11 in the power equation?
Oh, okay.
Constant?
So this data logger only records up to 2,500 millivolts, which is 2.5 volts. The solar panel actually produces at a max capacity about 17 volts. So in order to get it to a value I could record, I had to use a voltage divider of so 100K resistor here and 10K resistor here gives me a division of voltage of about 11. Well, not about 11. So the voltage I actually recorded times 11 would give me the actual voltage across the solar panel. Yes?
When you were discussing your torsional analysis of your wheels, you said you experimentally determined the amount of, I think, pound force that it took to cause one wheel to basically overcome the friction and rotate. It was like somewhere around 3
Yeah,
pounds.
okay, so
Can you describe that, how you experimentally determined that for
for
each
the
wheel?
rolling resistance?
Yeah.
For the rolling resistance of the wheel, it turns out I took I divided up the weight into 56 pounds per wheel. So I took 56 pounds of weight, attached it to the bearing of one of the wheels, and put it on a concrete surface because that's what it's going to be rolling on. And then lifted the angle of that concrete surface until it finally rolled.